Welcome back, everyone. Today we are diving into an explainer on section 20.3 of your software engineering text. And honestly, this is where things get really interesting, because we're going to unpack why the traditional engineering methods you've probably been taught completely fall apart when it comes to modern software. We're looking specifically at a concept called reductionism and how it interacts, or rather, fails to interact, with complex systems. This is an absolutely crucial part of your course because it's going to fundamentally challenge how you think about building software. So let's just jump right in.
We've got 6 key areas on our agenda today. We'll start with an introduction to reductionism, see how it applies to software engineering, and then look at exactly when and why it fails. After that, we'll break down the 3 false assumptions of reductionism, explore why software makes things even more complicated, and wrap up with a summary to help you prep for your exams. All right, let's kick things off with Section 1, the philosophical foundation of engineering, which is reductionism. Before we can really understand why something fails in modern software, we have to understand the foundational rule that has successfully governed almost all engineering for centuries. You'll definitely want to take note of this formal definition. Reductionism is essentially an engineering approach that relies on breaking down a massive, complex problem into smaller, manageable subproblems. You solve those subproblems independently, and then you just integrate the solutions back together to fix the larger issue. It's the assumption that a huge system can be completely understood and built just by decomposing it. You build the individual parts, you snap them together, and boom, you have your whole system.
And you know, reductionism works beautifully in traditional physical engineering. Think about mechanical engineering, like building a car. It works so well here because the physical linkages are limited and highly predictable. You can build the engine in one factory, the body shell in another, and the drivetrain somewhere else entirely. Because the physical interfaces between those specific components are strictly defined, you can completely separate their construction and then easily integrate them later on the assembly line.
Moving right along to Section 2, let's look at how this applies to our field: 50 years of decomposition in software engineering. For the last half-century, software engineering has leaned heavily on this exact same approach. Just look at the methodologies we use every single day. Top-down design literally involves taking a high-level model and breaking it down into smaller components. Object-oriented programming, or OOP, relies entirely on decomposing a system into independent objects that encapsulate data and operations. Now, you might think of Agile methodologies as this modern, radical departure from traditional design, but surprisingly, even Agile is inherently reductionist. The only real difference is that with Agile, you're decomposing the system incrementally rather than all at once up front. But the crucial takeaway here is that all of these rely on breaking systems down into smaller parts.
So just to briefly recap where we are, reductionism is our comfortable, trusted, historical foundation. It's been the absolute basis for building predictable physical machines and independent software programs alike. Break things down, build the pieces, put them together. Simple, right?
Well, that brings us to Section 3, where we see the paradigm shift. This is where reductionism fails. Here is the inciting incident of today's lesson. What actually happens when we try to apply this comfortable rule to modern, massive architectures, specifically what we call systems of systems? A system of systems is exactly what it sounds like: a massive system containing 2 or more independently managed elements. In traditional systems, you have limited relationships that can be scientifically and mathematically modeled. But in a system of systems, you have unpredictable, highly dynamic relationships between independent software components. There are simply too many static and dynamic interactions going on at once. I mean, how do you predict the behavior of a whole system when the individual parts are constantly shifting and adapting? The short answer is, you can't. Reductionism simply breaks down.
Let's dig deeper into why this happens in Section 4, by dissecting the 3 false assumptions.
What we're looking at here perfectly replicates Figure 20.5 from your source text. It contrasts 3 wildly false reductionist assumptions: control, decision-making, and problem definition, against the messy, complex reality of systems of systems. We're going to go row by row and break these down step by step so you understand exactly why these assumptions fail in the real world.
First up, let's talk about control. Reductionism assumes that there's a controlling authority, a single owner, that can resolve disputes and make high-level technical decisions across the entire program. But the reality of a system of systems is that there is no single system owner. Different parts of the system are governed by totally different, independent bodies, and they each have their own rules, priorities, and management policies. You simply cannot enforce a single technical vision when you don't actually have central control.
Second, we have decision-making. Reductionism assumes that interactions between components can be objectively assessed. It assumes we're making rational, technical decisions driven by mathematical models or performance metrics, kind of like choosing a car design based purely on fuel economy. However, the reality in large systems of systems is that decision-making is driven heavily by political motives and organizational priorities. Because you have multiple stakeholders involved, objective technical logic often has to take a back seat to sheer organizational politics.
Now, before we tackle the third assumption, we really need to define a vital term: a wicked problem. A wicked problem is a scenario so incredibly complex, involving so many related entities, that there isn't even a definitive problem specification. Different stakeholders look at the exact same problem and see it in entirely different ways. Sometimes, the true nature of the problem only actually emerges as a solution is being developed. Think about emergency planning for an earthquake. You really can't know the exact boundaries or the specific needs of the problem until the disaster actually happens.
Which brings us to the third false assumption: problem definition. Reductionism assumes clear boundaries and a well-defined problem. If you are building a physical bridge, you know exactly what stretch of river it has to cross, right? The boundaries are physical, objective, and agreed upon. But the reality is that systems of systems are often built to tackle these wicked problems we just talked about. The boundaries are highly subjective, they are constantly being renegotiated, and they shift based on different stakeholder viewpoints.
So, to consolidate this crucial topic, reductionism completely shatters when applied to systems of systems because we lose central control, mathematical logic gets replaced by organizational politics, and clear, definable boundaries dissolve into subjective, wicked problems.
Okay, moving into Section 5, let's explore why software actually makes all of this even worse.
You might be wondering, if reductionism fails for complex systems in general, why does software specifically exacerbate these three failures? Well, there are three methodical reasons for this complication. First, relationships in software systems are not governed by physical laws, which completely prevents us from producing mathematical models to predict behavior. Second, software has literally no physical size limits, meaning boundaries can be easily and subjectively changed on a whim, making those wicked problems even harder to pin down. And third, and this is perhaps the most dangerous one, linking independent software systems together is deceptively easy. Because it is so technically simple to create an interface, we are far more likely to try and build massive federations of systems without proper governance, which just leads to uncontrollable complexity.
It's really vital to recognize this misconception. We often think of software's flexibility as its greatest strength, don't we? But because it has no physical limits and is so deceptively easy to link together, its intangible nature actually invites unmanageable complexity. We get tempted to build incredibly complex architectures that far outpace our human ability to actually manage them.
Let's wrap things up with Section 6, our summary and exam prep to consolidate everything from Section 23.
For your upcoming exams, you absolutely must be able to recall these core concepts. You need to memorize the definition of reductionism, breaking down a large system into subproblems. You must be able to clearly contrast the three reductionist assumptions from Figure 20.5 against the reality of systems of systems, the lack of central control, political decision-making, and shifting boundaries. Make sure you can confidently define a wicked problem. And finally, you must be able to explain the three reasons software exacerbates this complexity: no physical laws, no physical limits, and the deceptive ease of linking systems together.
I want to leave you with this final thought from the text, which bridges perfectly into our next lecture topic. Since reductionism has failed us for complex modern systems, we can't just try to improve top-down design. We need entirely new abstractions, methods, and tools that rely on probability and statistical simulation to help us navigate this. So ask yourself, if we can no longer control our software by breaking it into neat little pieces, how on earth do we build systems that are actually designed to survive their own unpredictable chaos? Think about that as you prep for your next class. Thanks so much for joining this explainer, and I'll see you next time.